and welcome back to Math and Engineering Help Desk for another illustrative math video. This one here is for lesson 11 on equations of lines. So finally we're getting into some x's and y's, some variables, some unknown quantities, and trying to put it all together with some of the earlier concepts that we have outlined in previous videos. So in this video we're going to walk through the student-facing task statements for lesson 11, which deals with coming up with equations to represent lines, and then we're going to obviously use this to build into the final lesson of the unit on which is lesson 12. So we'll get to that in due time. So here's the warm-up for this lesson. So we have a diagram here, and on this diagram we have two goals. Now the second one did not pop onto this slide here. We have two goals. We want to find how long this vertical segment right here is. Let's highlight this vertical segment. We want to find the length of this segment, segment BE, and at the same time we also want to know what are the coordinates of point E. Okay, so we want to know the x and y coordinates of this point right here. So ultimately, what are we going to do to figure this out? Well, recognize that we have a diagram that we're kind of familiar with. We have a triangle, a large triangle, and then we have a dilation of that triangle. And we can look at it either way, of course. We can look at triangle ABE as the original and ACD as the dilation, or vice versa. Whichever way you want to look at it is going to allow you to answer the question. So ultimately, we want to find out the length of segment BE. Well, if we recognize that this has got to be a dilation of this, if we find, again, using two different approaches, we can do two different approaches. If we find either the ratio of the side lengths between two corresponding sides of the triangles, or we use side length quotients to do that. And since the side length quotients is one that not everybody is familiar with, or not everybody is comfortable with, let's use that method to figure out what the length of BE is. So what I'll do here is I'll look at length CD, and I'll say, okay, well, how much distance is it between these 2 points? Well, you'll notice that in this case we have ordered pairs to go with where those points are, and we can use those ordered pairs to figure out lengths. In previous problems we've had grids and we can just count grid lines. Well, here we've got ordered pairs. So in order to use ordered pairs to figure out how long it is, we need to know the difference between these points. So in other words, we need to know in each case what the y coordinate difference is and what the x coordinate difference is. So we would want to know change in y, and then at the same time we would want to know, let's actually underline this. We want to know the change in y, but we also need to know the change in x, all right, to kind of get that idea. So, and you know, it's similar to slope, but notice that here the change in x is nothing, right? So there's no change. So we can ignore that completely and just focus on the change in y. So the distance of this line would be the difference between 7 and 2, which is 5. So the length of this line, segment CD, is 5. So we can use that same principle to look over at AC, because we would need to know that as well if we're going to find out what BE is. Well, AC, we have 0, 2, and 4, 2. So if I use that same principle, there's no difference in y. So that's why I can tell it's a horizontal line. But 0 to 4, that's a distance or a change of 4. So the distance of AC, that's a 4 unit long segment, right? So with that in mind, we can then say, well, the side length ratio from CD to AC is 5 over 4, right? So we say 5 divided by 4 is our side length ratio, 5 over 4, okay? Now, with that in mind, we can then use that same principle to figure out what's going on here with BE. Well, AB, that's 0, 2 to 2, 2. Again, no change in y. We have a change in x, though, of 2. So segment AB, that's a length of 2. So we can see right here that with unknown being BE, let's call that x, we can set up a proportion. We can say, well, 5 over 4 is equal to x over 2. So right away, we can see from here that we are going to have a proportion, that we can cross multiply and solve. So if we did 4 times x and 5 times 2, that would equal 4x equals 10, which means x equals, 4x equals 10, so it means x equals 2.5, okay? So we would divide 4 on both sides, right? So if we look at this, remember we cross multiply, we get the cross products, and then we divide by the coefficient of the variable to get the unknown in most proportions. Now, like I said, this is only one of many ways that we can approach this problem. Another way to look at this problem is also recognize that this large triangle and this small triangle, they vary by a factor of 2. So 2 to 4. So if they are similar, which they are, we've talked about that in prior lessons about why they're similar. So if this is 2 to 4, we think, well, x and 5, these got to be at the same ratio. So this number here has to be half of this. So that's why it's also 2.5. So you can go either way and go with that. So now, here's the hard part. That's 2.5. This segment right here is pretty much right in the middle. So if I look here and say, well, A is 0, 2, and D is 4, 7, well, what would the middle of that be, right? So I would look at x and y and I'd say, okay, well, x from 0 to 4, that's a change in 2. And also I can look here and see, recognize that the x-coordinate is exactly the same as this, right? So the x-coordinate has to be 2. And then we got to think that that's going to be 2. And then for the y-coordinate, we can use the same kind of logic. We can say, well, the y was 2 and it's now 7. What's halfway between that? Well, I can figure that out if I add these two and divide by 2, like taking an average kind of thing, which is the same way you would find a midpoint of a segment, by the way. 7 plus 2, then divided by 2, that's 4.5. So the y-coordinate here is 4.5. And again, there's a couple other ways that you can approach this particular segment as well. Another strategy here is to look, hey, you've got the line length of 2.5, which we found earlier. If we think this is a vertical line, we would just be adding 2.5 to 2, right? So 2 plus 2.5, that equals 4.5 as well. So we can look at it a couple of different ways to verify that indeed it's 4.5. Okay, so that's not easy. What we just talked about is definitely not easy. It mixes up the dilations with similar triangle principles, with slope and coordinate planes, and ordered pairs. There's a lot going on with this particular problem. So if you need to hear some of it again, please rewind the video and check it out. Okay, now we're going to move on, and we're going to go ahead and take a look at this next concept. Again, this is another kind of tricky concept, and we're going to explain this and show. Your teacher most likely would have done a lesson on this as well, and used this idea to explain how lines and coordinates and ordered pairs work. So now here what we have is a line that goes through the origin on the graph. Remember, the origin is 0, 0. The ordered pair is 0, 0. It's basically where the axes intersect, the x and y axes. So this line goes through the origin. We have point C, and we have point B, point D, and so on. Now, the first question is super easy. What is the coordinates of point B and point D? Well, point B, we can just look at the graph. We can say it's 4, 3. Okay, so the x coordinate is 4, and the y coordinate is 3. Okay. So that's easy. We could use the text tool for this. Let's do that real quick. Sorry. All right, let's use the text tool. 4, 3. Okay, so x is first and y is second. And then the point D, again, I can look and see it's 8, 6. Okay, so the x coordinate is 8 and the y coordinate is 6. Now, the question that asks you next is point 20, 15 on the line? Now, some students might say, oh, well, the graph only goes up to 10, so, why would it be on the line? Well, remember, a line extends forever in all directions, right? So this line would go beyond this graph. So you have to figure out, and also note the axes also continue, right? So those are lines as well. We'd have to figure out, is this point on the line? Well, there's a couple strategies we can figure out to identify this. One thing is to recognize that we have a line that's got some sort of slope, right? Every 4 units in x is a 3-unit change in y. So if I look at the origin 0, 0, and I look at this point B, 3, 4, which is sort of the first point I have in the line, and I see, well, the y changes 3 and the x changes 4, so we can express the slope as 3/4. So the slope of this line equals 3 over 4. Okay? So I can then look and say, well, does the point 20, 15 kind of fit that ratio, right? If I go 15 on y, is that the same as going 20 on x if the slope is 3 over 4? So I can test really quick. There's a couple of ways you can go about this. One is to recognize that the y should be 3/4 of the x. Another way to look at it is if you set up a proportion. You can go 3 over 4. And we can say, well, does that equal? I'm kind of writing this proportion differently here. 3 over 4, does that equal, excuse me, equal, that's what I'm trying to write there, does that equal 15 over 20, okay? Recognizing that we'd really be kind of seeing if these cross products work out, and if they are equal, then we indeed have a proportion. Well, 3 times 20 is 60, 4 times 15 is 60 as well. So these cross products do equal. That means that these are proportional, which then of course means that we would get on line 15, we would get on the ordered pair 2015 with this slope of 3/4 through this point here. Okay, so there's like I said, that's one of the many ways that you could explain this. If we were to continue using the same pattern of 4, 3, 8, 6, if we were to go to the next point that would kind of behave like this, it would be 12, 9, and the next point would be 16, 12, and then the next point would be 20, 15, right? So we could keep that pattern going and explain it that way as well. It would be a little bit more cumbersome to use that same logic with 175, however. If we use the same idea between proportions, let's say that, let's kind of extend this and say, well, would it be the case of having it being 75 over 100? Well, again, if I use the cross products principle here, 75 times 4 is 300, and 100 times 3 is also 300. So this indeed, yeah, this is right, okay? So these do check out. So again, you can kind of explain it with cross products. You can also explain that, look, the y, 75, that's 3/4 of the x, 100, which is kind of how we have to explain that, okay? And I want to write that out just to kind of explain what we're doing. The y is 3/4 of the x, right? Which means if we kind of turn this into an equation, y equals 3/4 x, right? Let me put the fraction in parentheses just to emphasize. 3/4 x, okay? So if I kind of look at it this way and write it out as an equation, I actually now, without even kind of realizing it, I've now explained the relationship between x and y using this coefficient of 3/4. So what you see right here, you may have never seen something like this before. This is a linear equation. This is a relationship that is produced by a line. So what you see up here, that line is produced with this equation. Every x is 3/4 of, or sorry, every y is 3/4 of the x. So no matter what, if I plug in an x value here and take 3/4 of it, I get the y coordinate for the point that's on that line. And that works for every single number that you can come up with. So again, now that I've kind of recognized that, I can explain that same idea with number 4. Is the point 90, 68 on the line? Well, if I were to take 3/4 of 90, would I get 68? Well, if I do 3/4 of 90, that's going to be, well, let's see here, that's 27 minus, that's going to be 63, okay? So it's not, right? Because they want to see if it's 68. So if I were to graph this line all the way into the x equals 90 area, the point that's on the line is actually below this point right here. So recognizing that if I took 3/4 of 90, I would not get 68. Now, if I know in the x and the y coordinates of the point, write a rule that would allow me to test whether the point is on line j. So what you see here, this is sort of the rule that you might come up with. You may even come up with it in words like this. You may recognize that the ratio between the y and the x is the slope. So there's a lot of ways that you can explain that, but this is kind of a useful lesson on that. All right, now, so like I said, this kind of works because the line goes through the origin. Now, the next bit of information, this one here is a little trickier, okay? We're going to complete the diagrams so that the vertical and horizontal segments have expressions for their lengths, okay? So now let me see if I can make this, zoom this in just a little bit here. Let's see if we can full screen that. Okay. Make this, I'm trying to make it a little bit bigger. I can make this diagram, expand this. Let's do that. And this one too. Okay, let's try to overlap those. Okay, now we're going to complete each diagram so the vertical and horizontal segments have expressions for their lengths. So this is a kind of part that hopefully we'll understand and follow here. Now, point E has coordinates of x and y. So if I want to know what the length is of these segments, I have to use the realization that I've got a point that's on the line and another point that's also on the line, but this point here is expressed with variables. So what would the length be? If I were to go from D to F, what I would do is I would have to do the x coordinate of this point, which is the same as the x coordinate of this point, right? And I would have to subtract that from the x coordinate of D. Well, the x coordinate of D is just 0. So if I were to write this, I would write here x minus 0, right? Whatever x happens to be I would subtract 0, which again is kind of counterintuitive if you understand identity properties. Subtracting 0 doesn't do anything, right? So really, I could just say that the length of df is x, right? And let's kind of write that out as a note down here. df equals x, right? Whatever the length of df is equal to that coordinate of x. Now for point f, that same principle works here as well. Well, we have the x coordinate. We don't need the x coordinate. We just need the y coordinate, right? Well, the y coordinate is 1, and the coordinate at this point is y. And so the difference between those would be the length of fe, which means that this distance here is y minus 1. So that would be for length fe. Okay, fe equals y minus 1. Okay. Now, same deal here. We have a length here 4. We have a length here 3. Here's another example. This time here we have a length 4. We have a length 3. And we'll use this realization in just a second to kind of come up with an equation. But we'll do this triangle here as well. So we have df. Let's use the same principle. Okay. E is a point that's on the line with x and y as its ordered pairs. If I look at df, well, the x-coordinate of df from point D is 2, and the x-coordinate of f is x, so the difference between those would be the length. So that length would be x minus 2. Whereas here, the point from f to e, well, the y here is y, and then the y-coordinate of this point is 4, because we use the y-coordinate from D, so that difference is going to be y minus 4. Now, what you're going to recognize about similar triangles is an equation for the quotient of the vertical and horizontal side lengths. This is going to allow you to come up with an equation that represents this line. Okay, so the equation would look kind of like this. Recognize that the slope is 3 over 4. Okay, so for this line right here, the equation that would represent this line would be the quotient of the vertical and the horizontal side lengths. So the vertical side length here is y minus 1. This is for the first line on the left here, y minus 1. And the x is just, we can write x minus 0 just to emphasize that we're talking about the x and the y here, right? So that would work. That would be for this one right here, this line on the left here, so this right here, right? Y minus 1 over x minus 0. So the difference between the y and the x. Same deal here. We would use the same 3/4 setup, okay? That would be this. Let me grab this and duplicate this. Let's, where's my clone? No. And there's a way to clone it, make it another copy. Sorry. That's just type it again. All right, so for this one here, same 3 over 4. And that's our slope. And why is it 3 over 4, by the way? If you still look at this other triangle, the vertical side is 3 over 4, so we know the slope of this line is also 3 over 4. So we set an expression for the slope, and we say that the y-coordinate of the line is y minus 4. Oops, I'll underline that. And the x-coordinate is x minus 2. Okay? So again, that's an expression for this line, right? So coming up with some relationships to go with that. And then lastly, one more example here. And let's grab these questions and kind of bring these to the front. Which one is it? This one? No, it's this one. There it is. Okay. Why the slope is 3 over 6. Okay, so if we look at this point here, now, why is the slope 3 over 6? Well, 2 over 6 in this case. If I look and see that the slope, that the line has a x-coordinate, y-coordinate right there, we see that it's 5, 7, and the x-y pair of this particular point here is going to be 7, 9, right? Oops, I forgot the parentheses. 7, I'm sorry, did I say 7? I'm sorry, it's not 7. What's wrong with me? Sorry, 5, 6, 7, 9, 11, 12. 12, 9. No, it's not 12, 9. It's, come on, Mr. Let's see, 6, 8, 10, 11, 9. Okay, my apologies. So, because the ordered pair here is 11, 9, and I could use another ordered pair over here if I wanted to, the difference between the x and the y is 2 for the y and 11 for the, 6 for the x. So if the slope is 2 over 6, that means the slope is 1/3, right? So we can see that the explanation here kind of justified by having the line be, the slope be 2 over 6. So if I go right 6, up 2. Now, horizontal, vertical sides of the triangle with the expression that represents their length. So once again, we can kind of see here that we're going to use, for the vertical side length, x minus 5. And then for the sorry, that was the horizontal side length, not the vertical side length, my fault. And then the y coordinate would be y minus 7. So once again, y minus 7, x minus 5. It equals to 6 because that's the slope of the line. And then these side lengths, vertical and horizontal, is the same kind of side length quotient. So hopefully that works for you, and this explanation in this lesson kind of gives you an idea of how equations of lines are kind of started with being created. There are obviously more simpler ways to write these equations and come up with different forms of them, and we'll talk about this in a future lesson, but hopefully this kind of helps you make sense of what the equations might look like. So hope this lesson was good for you, and I hope that you are enjoying the curriculum, and I hope that you have a wonderful rest of your day.